Welcome to Chapter 9. We're going to start in about halfway through Chapter 9 with polar coordinates. So hopefully you have the notes in front of you. We're going to go through and just do some practice problems. So when we're graphing polar graphs, we basically need an r and a theta. So a radius, that's what the r stands for, and the theta is the radian or the angle. With that said, what the graphs are going to look like, or the axes, if you want to think about it that way, is they look like concentric circles, so that each circle moving out from the center has a radius 1 greater than the previous one. So with our circles here, each one of these circles has 3 concentric circles, where the first one is radius of 1, the second one is radius of 2, and the third one is radius of 3. You'll notice that I only drew these out to 3 because the information that was given to me in the points each have a radius of 2. So I only really needed 2 circles, but I figured I would make it just a little bit bigger so I had some room to work. So my first piece of information here, taking a look at the point itself, what's being told is that the radius is 2, so I want to be on the second ring. And my angle, or my theta, is going to be pi over 6. So I want to find the point where I'm at the angle of pi over 6 and I'm on the second circle itself. So what I'm going to do is I'm going to go ahead and draw the line segment that pi over 6 looks like it's at. So starting from the center and working my way out, I have about there, kind of looks like pi over 6 to me. So now I've just satisfied the pi over 6 radian, so I may as well just go ahead and identify that. Now what I'm looking for is I'm looking for the location where the pi over 6 and the second circle meet each other. So I think that looks like it's about right there. So if I were to graph 2 comma pi over 6, this would be my answer. I'm on the second ring and I'm on the pi over 6 radian. Well, let's move on to the next one. So now, this one has a little bit more that we need to talk about though. So there's definitely an issue here. First part tells me that my radius is -2, and that doesn't really make any sense. So what I'm going to do is whenever I have a radius that's a negative number, I'm still going to treat it like it's a regular radius, but I'm not going to plot the point. I'm going to mark the point instead. So I will mark on the ring. I'm not going to actually plot. There's a little bit of work that we need to do. So we need to make sure that our radius is positive. It doesn't make any sense if our radius is negative. And then our theta is going to be pi over 4. Alright, so I'm going to go to where pi over 4 is, do exactly what I did before. Go to where pi over 4 is, and I'm going to draw what looks like the line segment. So pi over 4 looks like it's about there. That looks pretty dead center inside of the first quadrant. Then I'm going to go ahead, take out my color, and I'm going to go to where pi over 4 is located. I'm going to go to the second ring, and I'm going to mark it on the picture. I'm not going to actually plot it, I'm just going to put a little mark there. So second ring on pi over 4. So about right there is where it would be located. However, I want my radius to be positive. So what's kind of nice, actually really nice about the polar graphs, is to guarantee a positive radius, all you have to do is shoot through the pole. The pole is the origin. So I'm going to take this straight line segment of pi over 4 and I'm going to shoot it from the origin straight through to the other side. So what I'm doing here is I'm shooting through the pole. That is what it's called. So just so we can see what's happening here, I'm going to draw myself some arrows. So I'm going to take this and I'm going to shoot it through the pole, and I want it to be equidistant on the other side. When I shoot through the pole, I am turning the sign from negative radius into a positive radius. So I'm going to go the same distance. So from blue to pole is 2 circles. So from pole out, I have 2 circles. That's the actual location of this point. Now, I know that you might be a little hesitant to believe this, but what's nice about polar, and is not the same thing with rectangular, is that there are an infinite amount of points, polar points, that actually share the exact same location, where we've got the negative radius, if you want to think about it that way, in blue. So our blue, just kind of color code this here for us, is our negative radius. Whereas our red is if we have the positive radius. And the actual location of this point is at the positive. So we want the positive location. But just know that anything identified at the negative would still get shot through to go to the red. So with that said, let's take a look at another question. So here I have a little bit larger value, so you'll see that I put more concentric circles, and I've got a 2 pi over 3. So I'm going to do exactly what I did before. I'm going to go to where 2 pi over 3 is approximately, and I'm going to go ahead and sketch that out. 2 pi over 3 is pretty steep, so it looks like I'm about there. And then I take a look at the radius that was given to me, and it's not right on a circle, but that's okay. You can be between 2 circles. So just remember that there's a whole bunch of other circles in here that have a radius that isn't necessarily a whole number, and that's fine. Since it's positive, I'm going to go ahead and color it in red. It's the actual location. So I'll go out to the 3rd ring, so 1, 2, 3, and then I'll go a little bit less than halfway to the 4th ring. And I'll go ahead and plot that in red. So that's the actual location. So what I want to do, now that I have that, is I want to come up with a couple other points. Remember, there are an infinite amount of points that share the same location. So let's say that I want to just land directly on the red dot. So let's go ahead and do one with a positive radius. And then we're going to go through and do that whole shooting through the pole business. So positive radius. So I need to keep the 3.4. So I want to be on that ring still. And now I just want to land at 2 pi over 3. So in this case I can just do coterminal. So 2 pi over 3, and you could do plus or minus, doesn't really matter. Let's do a plus. So 2 pi over 3 plus 2, well, 2 pi is the same thing as 6 pi over 3. So if I do 2 pi over 3 plus 6 pi over 3, I'm going to get 8 pi over 3. So if I were to graph this point, I would land at the exact same location as the current red dot. Alright, well, let's do at least one negative radius so we can practice the whole shooting through the pole. And then one more after that. So you notice I left some space between the negative radius and the positive radius. I haven't quite decided what I want to do yet as my 3rd one. So I'll go back. I'm going to grab that blue color again like I did previously. And I want to shoot through. So I'm going to do the same thing I did. I am going to grab that 2 pi over 3 and just extend it down. So I'm going to shoot through about where it was. I want it to look like a straight line. That looks pretty close. I also know that I am going to be shooting through to go backwards. So I'm trying to find where the negative would be. And I want to go the exact same distance, so I'm going to be at that 3 pi over 4. So let's see where that should be. So I'm going to be at, 2 pi over 3, 3.4. So I want to go 1, 2, 3 and some change, and just stay right on this line. I'm not going to plot it, I'm going to mark it. So for me, whenever I mark something, it's reminding me that that's where the negative radius is. And when I plot something, that's where my positive radius is. So for my negative radius, I now need to turn my 3.4 into a negative 3.4 because I just shot through. And then taking a look at that location, when you shoot through the pole, you're going exactly pi distance. So if I take my original 2 pi over 3 and I add pi to it, well, pi is 3 pi over 3, that's going to give me 5 pi over 3. So these 2 points share the exact same true location, the red dot, as the original one. And I think I'm going to go ahead and do another negative radius, just because I've got the blue plotted already. So I've got negative 3.4 still. And instead of doing 5 pi over 3, I can actually do a negative angle. So starting from my positive x-axis and working back, or doing coterminal, this is going to give me a negative pi over 3. So all 4 of these, the original point, the positive radius, and the 2 negative radii problems have the exact same location. Alright, now we're just going to convert a little bit. So I'm going to make sure I have polar, which means that the first part is going to be my r, and the second part is going to be my theta. So it's at this point where I'm trying to create some ordered pair that is x, y. So I go through my equations, and I know that out of the 4 equations that I have, the 2 more straightforward ones to find x and y are the r cosine theta and the r sine theta. So I'm just going to plug in what I got. So my r is 2, and my angle is pi over 3. I'm just going to go ahead and do the math. So cosine of pi over 3 is going to be a half, and then 2 times a half is just 1. So there's my x. Let's go ahead and put that in the point itself. Then I can do the exact same thing for the y. So y is equal to r sine theta. So y is equal to, I still have a 2. My angle is still pi over 3. And if I go through and evaluate that, I'm going to get 2 times, well, sine of pi over 3 is root 3 over 2. The 2's cancel. I just get root 3. So there's my y value for the point. So now I've converted my polar into rectangular. Now, interesting note, with polar, there is with polar, there are an infinite amount of points that share the exact same location as 2 comma pi over 3. With rectangular, there is exactly 1 point that shares the location, 1 comma root 3. There's nobody else there. So I'm still dealing with the polar to rectangular. So I just do the exact same thing that I did a minute ago. So just plug it into the formulas, see what you get. So I went through, I plugged in my r and my theta into the exact 2 same formulas. I have my x and I have my y. So all I need to do now is just write it as a point. And remember that there is exactly 1 point at this unique location. So rectangular is unique, 1 value or 1 point, polar, not so much. There's a whole bunch of them there. Okay. Well, let's go the other way now. So we want to go from rectangular to polar. So in this case, I have an x and a y, and I'm trying to get to r and theta. So I want to get to some r and some theta. Alright, so I got to do a little bit of work. Now, if you take a look at your notes, there's actually 4 equations that help us go back and forth or convert between polar and rectangular. So when I have x and y and I'm trying to find r and theta, I use the other 2 formulas, typically. So I know that the first one I have is that r is equal to the square root of x squared plus y squared, which hopefully looks familiar to you anyway. This is just the Pythagorean theorem trying to find the hypotenuse in a right triangle. So if I plug my stuff in, I know that I have this big square root of, and my x value is root 3 squared plus, and my y is -1 squared. Let's extend that bar. So this gives me, well, the square root of 3 squared is just 3. -1 squared is 1. That gives me root 4, but root 4 is just 2. So I know my r is going to be 2. Then I need to find my theta. So the other equation that I use is the tangent. So tangent of theta is equal to, well, y over x. When I do the tangent theta, I like to get a quick sketch of where this root 3 common -1 is. And it's just to ballpark it. I don't need it to be perfect. So it's just my sketch of the original point, root 3, -1. I just want to know what quadrant I'm in so that when it gets to picking which radian I'm dealing with, I know where I am, quadrant 1, 2, 3, or 4. So root 3 is positive, -1 is obviously negative, so I think I'm going to be in the 4th quadrant. So I'm down here somewhere. I don't know exactly what that radian is, that's why I'm going to do the tangent. But I do know that it better be the tangent in that 4th quadrant. So go back to my problem. Tangent theta is equal to, my y is -1, my x is root 3. And if I go through and rationalize this, that gives me -root 3 over 3. So based off of my picture and my knowledge of tangent, this is located at 11 pi over 6, or -pi over 6. Either one is fine because we know with polar points you have an infinite amount of them. So I chose the 11 pi over 6 for this one. You could have chosen -pi over 6. It's the exact same thing. So here I've converted from my rectangular now to my polar. All right, let's convert some equations. It's the same idea. You're not converting points, but you're still using those 4 conversion equations for this. So for this one, I have r, and I'm trying to get x and y. So no r's and thetas anymore, x's and y's only. Well, I know of an equation that uses r, so I'm going to plug that one in. So my r is 6, and I know that that is really just x squared plus y squared, using the formula from before. But let's go ahead and clean this up. So if I square both sides, I get 36 is equal to x squared plus y squared, which is just the equation of a circle with the radius of 6, which is exactly what was given to me in the first part, r equals 6. So you want a radius of 6. Doesn't give you an exact location, so we want them all on the circle. So the equation of a circle. All right, let's take a look at this one over here. I need the x's and the y's to go. I need r's and thetas to come in. So I think I'm going to use that x is equal to r cosine theta, and that y is equal to r sine theta. Now typically when we are trying to convert into a polar equation, ideally we want r equals in the equation if possible. And I think this one's possible. They both have an r in common, so I think I'm going to factor that out. And then, to get the r by itself, all I have to do is divide by that mess. So I'll get r is equal to 2 divided by all the stuff in the parentheses. So 4 cosine theta plus 7 sine theta. You'll notice the only variables in here or unknowns are r and theta. The x's and the y's are gone. That's how you know that your conversion is correct, or hopefully correct, assuming you didn't make any arithmetic mistakes. All right, this one's a little bit more complicated. Not a huge amount, still the same idea though. So I want to get rid of r and theta, and I want x and y to come in. So I'm going to get rid of that r. I'm going to replace it with the square root of x squared plus y squared. And then I get 2 over 1 plus, well, I don't have an equation that is specifically for sine theta, but I do have one I could use and manipulate a little bit. So I'm going to go off to the side here for just a second. So the one that had sine theta in it was the y equation. So y is equal to r sine theta. I can solve for sine theta by dividing by r. So I'm going to go ahead and replace the sine theta with y over r. Now, I'm not done yet because I still have that r in there. This r, I deleted it completely, my apologies. This r needs to go. So we still need to replace that. So let's replace him. So I still have my square root of x squared plus y squared. And the 2, the 1, and the y, which is good. Now get rid of the r. I'm going to use the exact same formula I did for the other r. So I get the square root of x squared plus y squared. I know it looks horrific. We're going to try to clean this up a little bit though. I think what I'm going to do is I'm going to put a denominator of 1 on the left-hand side. So I'm going to cross multiply. So I'll have the numerator, which was the guy on the left, square root of x squared plus y squared, times the denominator on the right, which was 1 plus y over that square root as well, equals, and the top, which is just going to be 2 times 1 on that diagonal. Okay, this is actually okay and valid to leave it in this form, but there is a little bit of cleaning up we can do. So I'm going to go ahead and distribute the stuff on the outside. So square root of x squared plus y squared times 1 is just the square root of x squared plus y squared. Plus, now this is nice, when you distribute, you're going to have a square root of x squared plus y squared over a square root of x squared plus y squared, which cancels. So all I have is y. And on the other side I have 2. Now previously when we did the polar problems I said that you typically want to try to get the r by itself. Well, in rectangular you try to get the y by itself. But because I have a y on the outside and a y squared stuck to an x squared under a square root, I don't think it's possible without probably some tears and pain to try to figure this out. So I think we're just going to leave it at that. So here we have taken something that was polar and we have turned it completely into something that's rectangular. If you have any questions, make sure you ask in class.